Okay. Question 1 here is going to be solved using integration by parts. So we need to figure out values for u and for dv. Now, the guidelines for choosing a value of u, you want to make sure you choose a term whose derivative is a more simple expression than what you start with. So if we let u equal the natural log of x, then du is equal to 1 over x dx. dv then has to be whatever else is left. So I'm going to make dv equal to x to the negative 1/2, which is just the square of x on the bottom. I've just moved it up, given it a negative exponent. So then v, the antiderivative of this, is equal to 2x to the 1/2. Make sure that term is the dx. So, and the reason that we can tell that integration by parts is going to work is that by using u and dv, we're able to account for all of the terms. This is the u right here. If we thought about this integrand written as natural log of x times x to the negative 1/2 dx, and this part right here is u, this part right here is dv. Since the whole entire integrand can be represented by using u dv, we can use integration by parts. So the formula says the integral of the original expression is equal to u times v minus the integral of v du. That's going to equal natural log of x times x 1/2 minus the integral of v. I'm going to move the 2 out front, times du So simplifying this a little bit, we have natural log of x times x 1/2 minus 2 times the integral this right here, x to the 1/2 times 1 over x. This can be simplified as 1 over x to the 1/2, or it can be simplified as x to the negative 1/2. dx. So simplifying further, we have natural log of x times 2 times x to 1/2 minus 2. Now the antiderivative of this is going to be x to the 1/2 times 2. Plus c. Now, just recognizing some like terms from here before we add the constant of integration. They both have a factor of 2x to the 1/2, so we could factor this out. That would leave you with the natural log of x minus 2. Then we could add the constant of integration. Question 2 doesn't need to be found using integration by parts. We can use simple u substitution. If u is equal to 6x, then du is equal to 6 dx. So we need to multiply by 6 right here, and then multiply by 1/6 up front. So this can become e to the u, and this can become du. So we can make a u substitution here. 1/6 times the integral of e to the u du is equal to 1/6 times e to the 6x. And we have our constant of integration. Now question 3, if we consider this in factored form, the denominator is x plus 3 times x plus 1. X plus 1 is actually cancelled here. So this is nothing more than the integral of 1 over x plus 3 dx, which is equal to the natural log of the absolute value of x plus 3 plus c. It appeared that we may have to do partial fraction decomposition here at the beginning, but it happened that they had a common term that canceled out. So much easier than it looked. Okay, question 4. This is going to have to be partial fraction excuse me, this is integration by parts, which means we have to choose a u and a dv, and again the guideline for choosing u is to have a term whose derivative is more simple. So if we end up having u equal to x squared, for example, then du is equal to 4x dx. Now this is a linear expression, we start with quadratic, so it is a little more simple. dv could equal e to the 2x, which means that v is equal to 1/2 e to the 2x. It's a dx right there. So using these two terms, the u and the dv, we can rewrite this integral as the integral. This is our u term right here. This is dv. So the integral of u dv is equal to u times v minus the integral of v du. So this is going to equal u times v, the 2 and the 1/2 would cancel. This is just x squared times e to the 2x minus the integral. And I'm going to move the 1/2 out front of v, which is e to the 2x times du, which is 4x dx. Now we can move the 4 out front to combine with the 1/2, so this equals x squared e to the 2x minus 2 times the integral of e to 2x times x dx. Now this is another integral that we have to do integration by parts, and we need to make the similar substitutions for u and dv. So for here, you're going to let u equal x, and dv is going to equal e to the 2x, which means that du is equal to dx, and v again is equal to 1/2 e to the 2x. So we have to split up this integrand using the same integration by parts formula, uv minus the integral of v du. So we have the original piece here, x squared e to the 2x minus, now we have to do v du, so v du is going to be x times 1/2 e to the 2x, and then there's this negative, there's this 2 that's in front, so we got to put that 2 in there, minus the integral of v times du. Now this v here is a 1/2, so this is e to the 2x dx. So this is x squared e to the 2x. Now if you distribute this negative 2, it would cancel with this 1/2 here, so this is minus x times e to the 2x, and then this negative 2 multiplied to this term here will turn it into a plus, and these cancel out here, so then we just got to find the antiderivative of e to the 2x, which is 1/2 e to the 2x. And we add the constant of integration. Okay, question 5. This also has to be solved using integration by parts. So we need to assign a u and a dv. So if we let u equal natural log of 3x, then du is equal to 1 over 3x times 3 dx. Now, dv has to be anything that's left over. If we let this equal u, then dv is equal to dx, which means that v is equal to x. So now we use integration by parts formula, which is u times v. So this is natural log of 3x times x minus the integral of v times du. Now the 3 here cancels. This is 1 over x dx. Those cancel. So we have natural log of 3x times x minus the integral of dx. So this is equal to natural log of 3x times x. Matter of fact, I'm going to put the x out here so we don't get confused. X times the natural log of 3x minus the integral of dx, which is x. And we have the constant of integration. Okay, question 6. It appears we may have to do partial fraction decomposition. However, if we let u equal x squared minus 8x, then du is equal to 2x minus 8, which is 2 times x minus 4. And recognize that we have an x minus 4 and the dx. All we need is the 2. So if we multiply by 1/2 and put a 2, and this becomes 1/2 times the integral of 1 over u du, and this integral of 1 over u du is equal to the natural log. So this is 1/2 times the natural log of u plus c. So this is 1/2 times the natural log of x squared minus 8x plus c. So again, we were able to find the integral without using partial fractions. In question 7, on the original one I sent out, there was a typo. It was supposed to be 2x squared times the natural log of x. So I've made the correction here. You might have something, I think, where it might have been e to the x, but it should be natural log of x. So this one's one that needs to be solved using integration by parts. And here we're going to let u equal the natural log of x and dv equal 2x squared dx. The reason for letting u equal natural log of x is that du is simply equal to 1 over x dx. So the derivative is a more simple expression than what we started with. And here, the antiderivative is 2x to the third over 3. So this is going to equal to 2/3 x to the third times the natural log of x. This is u times v minus the integral. And I'm going to move the 2/3 here. So it's going to be x to the third times 1 over x dx. So this is 2/3 x to the third times the natural log of x minus 2/3 times the integral of x squared dx. So 2/3 x to the third times natural log of x minus 2/3 times x to the third over 3. So finally we get 2/3 x to the third times the natural log of x minus 2/9 times x to the third plus c. Okay, question 8. This one actually can be solved using u substitution. If we let u equal natural log of 3x then du is equal to 1 over 3x times 3 dx, which is equal to 1 over x dx. So you notice we have the 1 over x dx right here. So that's our du term. Then if we let 1 over the natural log of 3x equal 1 over u, then this equals 1 over u du. The integral of that is simply the natural log of u plus c. So this is the natural log of the natural log of 3x plus c. Okay, question 9 needs to be solved using integration by parts. Now if we start with this, as u and then dv could be x dx, and du is equal to 2 times x plus 1 dx, which is 2x plus 2 dx. So this is a linear expression, which is a more simple form of this quadratic. So the derivative has become more simple, and then v is x squared over 2. So then the integral becomes u times v. This is x plus 1 squared times x squared over 2 minus the integral of v, we have a 1/2 out front, times times du, which is 2 times x plus 1 dx. Now that 1/2 can cancel there, so now we have x plus 1 squared over 2 times x squared minus the integral of x squared times x plus 1 dx, and this can simplify 2x to the third plus x squared. Now, cleaning up this term a little bit, right here, x plus 1 squared is just x squared plus 2x plus 1. That's being multiplied by x squared, and that's all over 2. So then if we distribute the x squared, we're going to get x to the 4th plus 2x to the 3rd plus x squared. That whole thing is over 2. So what I'm actually going to do is take the 2 and put it underneath each separate term. So what we're going to have this simplified is x to the 4th over 2 plus, now it's going to be 2x to the 3rd over 2, but that's just x to the 3rd, plus x squared over 2. This right here is just this expanded out. Then we minus each of these integrals. This is x to the 4th over 4 minus x to the 3rd over 3. Now combining like terms, x to the 4th over 2 minus x to the 4th over 4 is x to the 4th over 4. Now x to the 3rd minus x to the 3rd over 3 is 2x to the 3rd over 3. And then we have the x squared term, x squared over 2, and then we can add the constant of integration. Okay. So question 10 does need to be solved using partial fractions. So we have 3x squared plus 3x plus 1 over x times x plus 1 times another x plus 1, which is just x plus 1 squared. That's equal to a over x plus b over x plus 1 plus c over x plus 1 squared. This is the form of the partial fraction. Multiplying both sides by the lowest common denominator. would leave us with 3x squared plus 3x plus 1 is equal to a times x plus 1 squared plus bx times x plus 1 plus cx. Now choosing nice values for x, for example, if we let x equal -1, and then x equals 0, and then we're going to have to choose a random number for x, such as 1. Choosing x equals -1 was chosen because that'll make this term disappear and that term disappear. So if x is -1, the left side, -1 squared is 1 times 3 is 3. 3 times -1 is -3. 3 plus -3 is 0 plus 1. So we have 1 equals over here we have c times -1, which is negative c, so c equals -1. Over here, if we let x equal 0, then on the left side we have 1. And then this term is gone because b times 0 is 0, c times 0 is 0, so we'll be left with 0 plus 1 is 1 squared, 1 times a is a, so a is equal to 1. Now, even though x equals 1 is not going to cancel any terms, we can also substitute the known values now. A is equal to 1, c is equal to -1. So if x is equal to 1 on the left side, we have 3 plus 3 plus 1, which is 7. And on the right side, if a is 1 and if x is 1, 1 plus 1 is 2, 2 squared is 4, 4 times 1 is 4. And here, if x is 1, 1 plus 1 is 2, 2 times 1 times b is 2b, and then c times x is -1. Add 1 become 8, subtract 4 become 4, so 4 is equal to 2b, which means that b is equal to 2. So now we know the values of a, b, and c, so the integral of this and of that is equal to the integral of 1 over x dx plus the integral of 2 over x plus 1 dx plus the integral -1 over x plus 1 squared dx. So the first term is nothing more than the natural log of x. And this is 2 times the natural log of x plus 1. And then the last term here, we think about this as -x plus 1 to the -2 power. Then we increase this by a factor of 1, or by 1, that's going to become -1. Then you divide by -1, which is going to cancel that. So that's just equal to 1 over x plus 1 plus c. Okay, the last 3 problems come from section 6.4, improper integrals. And really what we need to determine is, do these diverge or converge? If it converges, then the limit or the area under the function can be found, which means that the integral can be evaluated. So this is equal to the limit as b approaches infinity of the integral from 1 to b of x to -1/3 dx, which is equal to the limit as b approaches infinity, and the antiderivative of x to the -1/3 is 3/2 times x to the 2/3. We need to evaluate that from 1 to b, so it becomes the limit b approaches infinity of 3/2 times b to the 2/3 minus 3/2 times 1 to the 2/3, which is just 1. Now, as b gets larger and larger and larger, this term continues to increase and get larger and larger. What that means is this diverges. So it is not possible to evaluate this integral. Question 12, this is equal to the limit as a approaches negative infinity of the integral from a to -1 of x to the -2 dx. So this becomes the limit as a approaches negative infinity of -1 over x evaluated from a to -1. So this is the limit as a approaches negative infinity excuse me, of 1 plus 1 over a. Now as a tends towards negative infinity, these values are getting more negative and more negative and more negative. 1 over -1, 1 over -2, 1 over -1/3, and so on and so on. This whole entire value, 1 over a, gets smaller and smaller and smaller until it actually starts to reach 0 as a becomes sufficiently negative. So this term disappears as we take the limit as a approaches negative infinity. So the expression becomes 1. And it converges because this limit exists. Question 13. This is equal to the limit as b approaches infinity of the integral from 4 to b 1 over x is natural log of x to the 3rd power. Now, to find this antiderivative, we need to use u substitution. U can equal the natural log of 3x. So du is equal to 1 over 3x times 3 dx. The 3's cancel. So it's 1 over x dx. So forgetting about the definite integral, if we were just to find the antiderivative, this would become 1 over u to the 3rd times du. And the antiderivative of that is 1 over -2u squared, which is equal to -1 over 2 times the natural log of x squared. So this is the antiderivative if we make the appropriate u substitution. So this is equal to the limit as b approaches infinity of -1 over 2 times natural log of x squared evaluated from 4 to b. This equals the limit b approaches infinity from -1 over 2 times the natural log of b squared minus -1, so that actually becomes a plus 1 over 2 times the natural log of 4 squared. Now if we evaluate the limit as b approaches infinity, the natural log of b as b gets larger and larger also gets larger and larger, but as the denominator increases, this fraction actually becomes smaller and smaller and smaller until it approaches 0. So this fraction actually disappears, and the limit as b approaches infinity becomes 1 over 2 times the natural log of 4 squared. So that's the value of the definite integral. And we see that it converges.